What if a black hole had a surface instead of a point of no return? That one change could rewrite how we think about the most extreme objects in the universe. A gravastar is the idea that something can look almost exactly like a black hole from far away, yet avoid the singularity at the center. On the outside, it would still bend light, warp space, and pull in matter with brutal force. That's why physicists care. Black holes are elegant in theory, but the center of one leads to a place where known physics stops making sense. A gravastar tries to keep the drama without the mathematical breakdown. The basic picture starts with a collapsing star. Instead of crushing all the way into an infinite point, the collapse would halt in a strange, ultra-dense state. In the simplest models, the core becomes filled with vacuum-like energy rather than ordinary matter. Around that core sits the most unusual part of all, a shell so thin and so strong that it can hold the whole object together. It's not made of familiar atoms in the way a planet or star is. The material is hypothetical, exotic, and unlike anything we have directly observed. That shell matters because it gives the gravastar a real boundary. A black hole has an event horizon, a point beyond which nothing escapes. A gravastar would instead have an actual surface, even if that surface is buried deep inside a gravity field so intense that it would be nearly impossible to notice from a distance. From the outside, that's the trick. Gravity doesn't care whether the interior is a singularity or a stabilized core. So a gravastar could still twist starlight, shape nearby gas, and look, for many purposes, like a black hole. The reason this idea exists at all is that singularities are unsettling. They are not just dense objects. They are signs that our equations are being pushed beyond the place where they can give a sensible answer. So gravastars were proposed as a possible escape route. Instead of matter being crushed beyond recognition, the collapse would reach an extreme limit and stop. Vacuum energy would provide the pressure needed to resist further collapse. That makes the inside of a gravastar especially strange. In everyday language, a vacuum sounds empty. In physics, it's not truly nothing. Even empty space can have properties and energy, and gravastar models use that idea in an extreme form. Inside the object, that energy would be compressed into a core that pushes back against gravity. The result is a delicate balance, with inward pull on one side and outward pressure on the other. If that balance works, the object can remain compact and stable. The big challenge is that no one has seen a gravastar in nature. So the question becomes practical. How would we tell one apart from a black hole if both are dark, compact, and deeply distorted by gravity? One promising answer is gravitational waves. When massive objects collide, they send ripples through spacetime. A black hole merger has a very specific pattern as the horizons combine and settle down. A gravastar merger could be different. Because it has a shell rather than an event horizon, it might produce faint echoes after the main collision. Those echoes would be subtle, but they could reveal that something is bouncing or interacting at the surface instead of disappearing forever. That's a huge clue, because black holes are expected to absorb incoming material past the horizon. A gravastar, by contrast, would have a surface that could respond differently to matter and waves. Astronomers are not looking for a dramatic visual difference. They are looking for tiny departures in the data, the kind that show up only when measurements are precise enough and the models are good enough to notice. That's why the debate matters beyond theory. Gravastars sit at the crossroads of gravity, quantum ideas, and stellar collapse. If one were ever confirmed, scientists would have to rethink what happens when matter reaches the edge of extreme gravity. Black holes are still strongly supported by observations, from stars orbiting the centers of galaxies to the gravitational wave signals already detected from mergers. Gravastars do not erase that evidence. They simply ask whether black holes are the only possible answer. For now, gravastars remain a serious possibility, not an established fact. Their power is not in replacing black holes today, but in challenging the assumption that the universe must end in a singularity. If nature allows a compact object with a hidden shell, a vacuum-like core, and black hole-level gravity on the outside, then the cosmos may be stranger than the name black hole ever suggested. Would you rather discover one in the data, or never have to explain what its interior really is?